next topic is differential equation solutions. So when you are dealing with integration, you will have only one function. Let's say maybe you will be dealing with let's say dy by dx is f of x. Then y is integral f of x dx. So up to this part we have seen how to perform this integration. But when you have differential equations, I mean the equation contains all orders of differentials, like your simple harmonic oscillator p square y by dx square plus omega square x omega square y is equal to 0. So these kind of equations. So to solve this, we may have to perform, I mean it's also kind of integration, but depending on the order of the equation, we need to perform it twice or thrice. I mean it depends on the order of the equation. So for a simple application, we consider this Picard's method. This is convenient for solving first order differential equations. Other things we will see for higher order terms. So let's say this kind of equation, I mean almost like numerical integration. So I am considering same dy by dx is f of x. So this is y prime. That is a given equation. I need to solve that, and for that I am considering a Taylor series expansion for y. That is y is equal to y0 plus h times y prime plus y double prime h square by 2 factorial plus etc. So this is the Taylor series, and I am neglecting all the higher order terms. So if I neglect higher order terms, I will be left with, so here y is a solution, right? So y is equal to y0 plus h times y prime. So this is the least possible approximation for the solution. Y equal to y0 plus h y prime. So I can write it as y is equal to y0 plus h times f of So to solve this differential equation, we need to know the initial condition. So that initial condition is y0. So this is the initial condition. So to solve the first order differential equation, we need to have one initial condition. If the order is of 2, we require two initial conditions. One is the value of function and first derivative of the function at 0. Okay, so we need to have an initial condition, and once you start substituting that initial condition, you can predict the future of the function. How the function evolves can be predicted. Okay, so I'm starting with, let's say I'm taking an equation. So dy by dx is 3x square plus 1. And initial value y0 is equal to 2. What is y2 is the question. Initial value of the function is 2. So we have to integrate it up to 2. So I mean, if you normally directly perform the integration, what is y? X square plus 1. That constant is, so it is x cube plus x plus 2. This is the function, and we need to get the value at 2. So what is that? 8 plus 2 plus 2. This is the exact result. So even consider, let's say initial value is 1. To avoid the confusion, I am considering the initial value to be 1. Then the result is 11. So what is the function? X cube plus x plus 1. Maybe the initial value is starting from 1 with x cube plus x. The function looks like that. And let's say I am considering h is equal to 0.5, h is equal to 0.25. Another possibility, h is equal to 0.1. I'll check the result predicted by the simple approximation. For h value 0.5, 0.25, 0.1. Okay, so what you have to do here? We have to start from here. So initial value is 0. Starting from 0, you have to go up to 2 with a step size of 0.5, 0.25, 1. So at every level, you have to get the value of new function and substitute in the next level. So let's say you are starting with 0 and your step size is 0.5. So what is the first iteration? So y1 is y0 plus f of x0 y0. So f of x0 y0 is 3x square plus 1. So y0 is 2. Now y0 is 1. Plus 3 into 0 square plus 1. So y1 is 2. So next one y2 is y1 plus f of x1 y1. So y1 is what? This is for 0.5. This is 1.0. So value of the function at 0.5 is that. Value of the function at 1.0. You have to continue this value. So it is 2 plus so what is this? 2 plus 3 into 0.25. Y3 is at 1.5. Y2 plus f of x2 y2. It is 3.75 plus 3 into 1 square plus 1. So 13, 14, 15 point. So this integration is actually area under the curve. So we are considering a curve 0, 1, 2. And we are considering an integration here. The result looks like that. this is the original curve and the result obtained for that is 11, and our linear approximation got a result of 15.5. So if you use a step size, you will get better and better solution. Then how to write a program for this? Let's say I'm starting with Picard. X initial value, X final value, and then F H. X is equal to X initial to X final with a step size of H. So initial value, final value and H value we get. Then do X is equal to X initial to X final with the step size of H. We have to initialize Y value. So I'm starting with Y is equal to Y0. Do X is equal to X initial to X final with a step size of H. Y is equal to Y plus F of X comma Y. We have to write that function. some cases that function may contain y value also. Here the problem we have considered does not contain any y. So f is equal to simply 3x square plus 1, but I am sending both the values of x and y as inputs to this function. Here we have to start from x initial plus h. No. X initial value 0. Initially we have substituted 0 and a particular y0 value. We have gone up to the last term. We have to check that. Minus h. So we have to go up to x final minus h. X initial to x final minus h with a step size of h. When we are starting from 0, 0 and going up to 1.5 here. 0, 0.5, 1, 1.5 to get the value of 2. So here also I have to start from 0 and go up to 1.5. X final value is 2, 2 minus h. So the do loop runs from x initial value to x final minus h with a step size of h. So here we are using real numbers in the do loop. So to compile that program we need to use this G95 minus f real minus loops and the program name Picard.f. So the variables used in the loops are real numbers. So we need to add that additional condition G95 minus f real minus loops space Picard.f. And then ./a.exe is to run the program. Make sure that your variable names you are using here contains underscore x underscore im and this is x underscore fi. And if you use minus, it will be considered as two different variables with a subtraction. So, rest of the topics we will see in the next session.